All right, so I was kind of working through some of this material in the previous video, and then my recording quit on me for some reason, and I didn't even realize that it had quit. And as you can see, I've already worked through some other stuff. So I'm going to just talk through what I did when I thought I was recording so that we don't miss anything. So here we were talking about how to tell if a function is differentiable at a point, or more specifically, not differentiable at a point, by looking for certain characteristics in the graph of that function. And things to look for if a graph is not, or if a function is not differentiable, is if the graph has a cusp or a corner, which we drew here. This is a cusp. It's when the graph kind of curves into a point like that, or where we have a corner, kind of exactly what you would think of as a corner. Discontinuities are places where graphs cannot be differentiable, and vertical tangent lines. So if the graph ever appears to go vertical at any point, we would have a vertical tangent line there. That would also imply that we have non-differentiability there. In order to understand why that's the case for some of these, we can kind of intuitively talk about it. So like, for example, functions have to be continuous to even talk about the derivative existing there in the first place. That right off the bat is necessary. But looking at cusps and corners, take the corner, for example. If you're looking for the derivative of this function at that point, remember we take a limit, and limits have to be able to approach, a two-sided limit has to approach whatever it's approaching from both directions. So when we take the limit as h approaches 0 from either the left or from the right, then remember we're approximating the, we're not approximating, but we're finding the slope of a tangent line by first looking at slopes of secant lines, by, say, connecting these 2 points right here. Or, if we approach from the right, connecting these 2 points with the secant line. But no matter how close I bring this point to that corner, I can see from this example that the tangent line the secant line will always be a positive slope. It'll always have a positive slope because this part is going uphill. Whereas if I approach from the right, these 2 points will connect into a secant line that has a negative slope. So my left-sided limit is going to give me a positive number, whereas my right-sided limit is going to give me a negative number. And so those two one-sided limits are going to disagree with each other. That tells me that the two-sided limit does not exist, so the derivative doesn't exist. Okay? And then finally, the vertical tangent line. Remember, when we talk about like slopes of lines in algebra, we say that vertical lines have undefined slope. Well, if the slope is undefined, that also means the derivative is undefined there, because that's what the derivative is. It's the slope of the tangent line there. So in all of these cases, we have non-differentiability. Down here was an example that I worked through when I thought I was recording and I wasn't. We have the graph of a function, f of x, and we're asked to find all the values of x for which f is not differentiable. I did that here. I did something here that I decided I didn't want to do, and I scribbled that out, so you can ignore that. You can ignore this too, that was part of that. So we're looking for these characteristics, right? I have a discontinuity here, that's at -4. I have a cusp here at -1. I have a vertical asymptote here at 2, and remember, vertical asymptotes are a type of discontinuity, so we would have non-differentiability there. Here, my graph appears to have a vertical tangent right here. It appears to go vertical right as it crosses the x-axis at 5. So all of those values, -4, -1, 2, and 5, those are all places where this function would be non-differentiable. Okay, just, again, looking for those characteristics. Okay, so the last thing that we're going to want to do is we're going to take a look at the graph of a function, and then we're going to try and graph its derivative just by using the graph of the original function. We don't have a description of the function outside of the graph to work with, so we can't apply the limit definition directly. So instead, we just want to look at what the characteristics of that function are and how they relate to the derivative, which we've already done a little bit of in this section. So here's sort of a guide for graphing the derivative of a function, f prime, if you see a graph of f. First, we're looking for important x values, and we can write them on a number line. Okay, so specifically, we want to look for x values where the graph has a horizontal tangent line, because we know that the function or the derivative will be equal to 0 at those places. Also, we're looking for for x values where f prime of x does not exist, places where the graph or the function would be non-differentiable. And we just looked at an example of that on the previous page here. Then we want to determine and record the following information on our number line. We want to look for intervals where the lines tangent to the graph of f have a positive or negative slope, as well as whether the slopes are getting more or less positive on each interval or are constant. Okay? And then we use the information on that number line to graph f prime. So to finish this section out, let's do this with this guy right here. Okay, we're going to create this number line. And we want to find first all points where we either have a horizontal tangent or a place where the function is not differentiable. So as I go from left to right, what I can see here is that I come to a cusp or a corner at this point right here. We know that that means the function is not differentiable there. It happens at -6, so I'm going to put a -6 on my number line. Okay? As I move to the right of -6, the graph looks kind of like a parabola. And so I don't see any issues. I don't see any issues until I get here to 0. At 0, at x equals 0, I have a big discontinuity. The graph breaks right there. So at 0, our function is not differentiable. Then we kind of proceed this way. We keep going, we keep going, and we keep going. And then we get to about 10. And at 10, I have what appears to be a vertical tangent. Okay, so at 10, because there's a vertical tangent there, the graph would not be differentiable there. I missed something important. I have one place where I see a horizontal tangent. It would happen right here at the vertex of that parabola, if that thing actually is a parabola. That appears to occur right here at -2, so I should include -2 on my number line. Don't worry about this stuff being accurately spaced. It's just about breaking our number line into these pieces so that we can analyze what's happening on each piece. Okay? Now, let's look at the interval from -infinity to -6. So on my number line, I have this interval right here. It looks like my function is decreasing that entire time. Okay? So f prime is going to be negative there, less than 0, because that's what it means for our function to be decreasing. In addition to that, the slope of this piece of my curve right here is going to be constant, because this is the graph of a line. The slope is not changing. It's always coming downhill at the same rate everywhere. In fact, that's a defining characteristic of a line. The slope is the same everywhere. So I would say something like constant slope there. Okay. Now in the interval from -6 to 2, what can I say about that? Well, as I go from -6 to 2, it looks like I'm doing a steep uphill climb that whole time. So that means f prime is positive there. Okay? It's positive there. So, but we need a little bit more information. It's not just that it's positive. You notice it starts off pretty steep, but then it eventually has to become less and less steep so that it can get to a slope of 0. So it's a positive slope, but it's also a decreasing slope. The slope is getting smaller as we go up. Once I hit that horizontal tangent, I made this a little bit too crowded, sorry about that. The slope actually continues decreasing and becomes negative, because now the function is decreasing. So f prime is negative because the slope is going downhill for this little segment right here. So not only that, it's going from 0 down into negative and more negative, steeper and steeper. That means that the slope is still decreasing there. Decreasing slope. Okay? From 0 to 10, what's happening? From 0 to 10, it looks like the slope is positive. I don't even have what looks like a horizontal tangent there. It looks like it's still kind of angled down. It's not a super steep slope, it's kind of shallow, but it's getting steeper and steeper and steeper until it gets vertical. Now, we said that means that the slope is undefined. Really what happens, though, is the slope is getting larger and larger and larger, and in a certain sense, it's almost like it's going to infinity right here. That's how we think of a vertical slope. It's that kind of undefined. Now, it doesn't actually get to infinity. Infinity is not a number, but that helps us to understand what's happening to the graph of f prime there. So f prime is positive there because we're increasing, and the slope itself is increasing. It's getting bigger and bigger and bigger, increasing slope. Finally, from 10 to infinity, my function is still increasing. So my function f of x is going uphill. That means f prime is still positive there, but it's getting like a shallower and shallower slope as we move to the right. Still increasing, but it's getting shallower. So I would say that the slope is actually decreasing, even though it's still positive. Decreasing slope. Okay? How then do we create a graph for this? So my goal here is to create a graph for f prime. Now, if I wanted to be super accurate, I would probably have, I'd have a grid here like I have up here to make it a little easier to graph things really, really precisely. But instead, I'm just going to kind of get the most important information down. So my number line right here, I want to make sure all of those values are indicated on my graph. -6, -2, 0 is just the origin. And then I have like 10 way over here. Not worrying about it being too perfectly to scale. Now I want to think from each of these, I want to think through each of these. So f prime is negative. And I want this graph to be the graph of f prime. So the curve from -infinity to -6 should be below the x-axis where we have negatives, okay? So it's negative and it's constant. Constant functions look like horizontal lines. If you actually look at this graph and figure out what the slope of that line is, find where the line intersects some points on the grid itself. So if you notice, to get from this point to this point, I go down 2 units and over 1 unit. If I think of slope as rise over run, that's -2 over 1, or just -2. So that means from -infinity to 6, I'm going to put a -2 here, I have a horizontal line and then a hole right there. It's a hole because my function is not differentiable at -6. Okay, I didn't draw that super well. This should be a little bit higher, but that should be like at -2. Next step, from -2 to 6, we have f prime, and it's positive, and it's not just positive, it's decreasing. So if you notice, it's at its steepest right here. That means when I graph this part of my derivative, the part of the curve that goes from -6 to -2 will be at its highest at -6, but then the slope, while still positive, is decreasing down to -2. So we're going to see something coming down like this. All right, so let's say it starts up here. I'm going to put an open circle there, and that's going to indicate that the function is still not differentiable at -6, so there should not be a point on the derivative here. You can approximate this slope by kind of thinking about the tangent line. So the tangent line, if I were to sort of sketch a tangent line here, it's a little tricky to do, but you can kind of get it. You know, use a ruler or something like that. But if you count, we have 1, 2, 3, 4, 5, 6, 7, 8. I think I kind of missed it right there. It's a little bit more like right here. So I'm going up 8 units over 1. That indicates that the slope of this tangent line right here is probably about 8. I'm going to put it at 8. Okay. However, it's also decreasing down to 0. So that indicates that my slope is going to be getting shallower and shallower and shallower until I get to a horizontal tangent right here at -2. Okay, so it's gonna do something like that. Now the slope is gonna continue going down, and actually it's gonna go below -2. It's gonna hit -4 here. And the reason I know that is because if I think about the fact that this has gone how far? From -6 to -2, it's going to total of 4 units. And then from -2 to 0, that's 2 units. That's half the distance that we went from here to here. So if I manage to drop a total of 8 units from here to here, I should drop half that from here to here, 4 units. Whoops, I just realized I was off screen that whole time. Sorry about that. But yeah, so what I'm trying to say is that because we dropped 8 units from here to here, and because we're going half the distance in the x direction here, we should go half of that 8 units from here to here down to -4. Okay, now the function is not differentiable here because we have a discontinuity. So I should indicate that with an open circle like that. Okay, now looking at what's on my number line, from 0 to 10, we have a positive derivative with increasing slope. It starts off really, really shallow. So it's even less than 1, because if the slope was 1, then I'd be going up 1 over 1, but that's not, it doesn't even appear to be that. So the slope is actually a little less than 1. Let's just put it right there. Right there. But as we approach 10, the slope is increasing, and it goes off to infinity because of that vertical tangent line right there. That indicates that at 10, we're going to have a vertical asymptote, okay? Then we kind of come out of that infinite slope, that undefined slope, and we're still increasing, f is still increasing, but our derivative is getting less and less because the slope is getting shallower and shallower. That's what we mean by decreasing slope here. So we're coming away from infinity, we're still positive, we're still above the x-axis, but the slope is getting smaller and smaller, and we're expecting something like that. Okay, so this is what I would put for my graph of this function. I didn't do a great job on this example because I kind of realized that I was working down here while you were looking at the graph up here and you couldn't see what I was doing. Hopefully you can make sense of everything I did though, now that you can see it all. That's going to wrap up section 2.2.